Istituto Italiano di Tecnologia, and MIT. And he will talk about
That was a very short talk.
learning with random features.
No, sorry, I've been sick for the last 2 weeks and my voice is going to go away in 3 minutes, so at least I can get some of it back. Right, so thanks a lot. It's a pleasure to be here. Thanks to the organizers. So I'm going to present some recent work with Alessandro Rudi, who's sitting over there, and possibly is going to expand on some of what I've been saying on Friday. I'm going to have just a very quick slide of blah blah motivation. This is mostly to set the tone of what I have in mind. And the whole motivation of this, I'm kind of in a grant mood in the last few days, so this is where this is coming from. And the whole idea is just, it's all nice and all with big data because you can do a lot of stuff, but there is a lot of cost. And here I just put two that I put in a grant that seemed interesting. The US data centers in the US cost roughly like 1 million houses just because of their number crunching, the amount of computation they have to do. And companies that actually want things to work pay something like 1,000 people to actually hand label images. So, the approach right now is definitely brute force. You get data, you just throw resources at it. If you're a big company, that's basically what you're doing. And if like me, I don't have a lot of resources, so I can ask myself, what else can you do? And you can try to do this roughly the same, ideally better, with less resources. And for us, the motivation is going to be mostly try to get a better interplay between statistical aspects and computational aspects. So a lot of things is exactly found in the same spirit of Alex's talk. You have optimization on one side, you have modeling stories on the other side, and oftentimes they proceed in parallel. There are a few people in the world that are trying to connect the two, but there is a lot of work to be done. And what I'm trying to show you today is one step in this direction. Then back to Earth. It's going to be basically a three-part talk. The first part is going to be about basically random features. You see it's just going to be basically a basic form of very simple neural networks. And then I'm going to try to tell you about the properties. First, I'm going to describe a basic case under very mild assumption, worst case. And then I'm going to tell you about more refined conditions, slightly more technical, that show more properties coming out. So the problem I have in mind is just the basic machine learning problem. This is just the picture version. You get some data, then you're given some new data, and then you would like to find a function that allows to predict for the new input the corresponding output. So it's a function approximation problem where you have input-output samples that are noisy, but also stochastically sampled. So there is both a sampling aspect and a noisy aspect. I'm going to be more precise in a minute, but this is just to tell you the problem. And so the first thing I want to introduce is the kind of function model we're going to consider. And they're not quite this, but almost. So these are basically shallow networks. This means there are linear combination of some nonlinear functions that are called activation functions. So here is just a linear combination with coefficient beta j of a nonlinearity applied to something like this. If you want, this basic operation here is the basic, it's called neural network because it's the basic representation of modeling of the computation in a neuron. I'm not going to talk about that at all. From a more practical point of view, what you have is that you define, the user define a nonlinear function sigma, and then the weights to be determined, there are parameters to be determined, and this says these are three sets of parameters. This beta j, the coefficient of the linear combination, this wj, and the bj, okay? Now, the story of this stuff is super old. Probably in the, the middle of last century, people start to come up with this idea. It had a very bad time around the 70s, essentially because it was impossible to train this kind of models, given the computational power they have. As you might know, things got a bit more practical lately. Paper like, in particular, this one paper here that somewhat set the tone for what was going to come in the last days here, basically show how you can put this kind of model to good use. And that number just gives you a feeling of the amount of impact that this kind of ideas had in the last few years. Going back to more theoretical aspects, this kind of shallow network has been subject to a lot of theory. Here I just mentioned three sources in case you want to start to pick up something. There is, on the statistical side, probably the book by Bartlett and Anthony contains a fairly classical account of properties. There is a very nice review by Pincus that has somewhat described the whole set of approximation results, very readable and encompassing a lot of things. And then there is the results by Barron that have both statistical and approximation flavor. They were all constrained to this, and and in many respects they're still state of the art for a lot of aspects. These are not quite the kind of network we want to consider. These network we want to consider are even simpler than this, basically because what we're going to do is that we're going to assume that the inner parameter of these networks are actually sampled at random. So we're going to replace, typically the inner parameter, all the parameters are chosen by optimization of some empirical objective function. Here we actually going to consider the inner parameter to be chosen at random according to the probability distribution which is given by the user, is predefined. Okay? So it's everything as before, but Wj and Bj are going to be chosen at random. As you can imagine, this also has a long history. Okay? The interesting part of this story is that in one part, these kind of ideas appear where you expect them to appear in the neural networks literature. Basically, in the early days, these things were proposed and somewhat abandoned because people were keen on trying to optimize things. There is this weird underground stream called extreme learning machines that also have tons of citation, and it's basically the same exact idea. There is a kind of a nicer connection to the fact that you can view this as a form of building some kind of sketching of your data and then a linear model on the sketch data. The sketching is non-linear. You can view this Wj and Bj, some of a sketching or an affine matrix, a random matrix that you hit, with which you hit the data and then you apply some nonlinearity. So if you look at things like 1-bit compressed sensing, they basically have this kind of flavor, this way of dealing with the data. And then there is a whole connection that connect these kind of ideas with Gaussian processes and kernel methods. This is actually something very classical. It's something that received a certain amount of attention. Probably the first person to point this out was Rashford Neal in '95. And then this trilogy of papers by Rahimi and Recht popularized this idea a lot, especially in the context of kernel methods. So this is the point we want to expand on. It provides the powerful tools of reproducing kernel Hilbert spaces to look at these kind of architectures, and that's why I'm going to spend a couple of slides discussing them. The basic idea is that we're going to look at the inner product of these numbers, and we're going to look at it as an approximate positive definite function. Okay? So you basically take the sum of these terms, and then I say that if m is large enough, if in fact if m goes to infinity, I can actually consider it as an approximation to this kind of function. This is an inner product, the expectation of an inner product between these two functions, and now big W and B are just the random variable according to which I sample Wj and Bj. Okay, so this is the basic idea. There are many examples for which we can make this precise. The initial one by Rahimi and Recht was basically showing that if you choose this function to be a cosine, and if you choose W and B to be respectively a Gaussian and a uniform distribution, then when you let Wj and Bj go to infinity, all you get is a Gaussian. And the proof of this is one line. It's basically just using the fact that the Fourier transform of a Gaussian is a Gaussian, and then some symmetry to go from exponential to cosine. So it's elementary. More in the neural network community, people, even after Rashford Neal, pointed out that there are other classes of nonlinearity and kernels that can be put in some kind of duality. And here, for example, if you want to this positive part and then again some distribution, you get some kind of kernel, is what is sometimes called an arc-cosine kernel. This doesn't matter too much, but it just gives you a feeling of some examples of this idea, okay? And this gives you now an idea that you can proceed in two ways. You can either start from random features or a network and ask what is the infinite limit, but you can also go the other way. You can start from a kernel and ask if you can build one or many random features associated to it. So this is what I'm trying to tell you here, just to take away the specific case and get a broad view. So when we talk about random features, the idea is that there's going to be a positive definite function lying somewhere, k, and then what we assume is that there is a random variable. So I drop W and B, I just take one, okay? And I take a very generic function phi, which is a function of both arguments, okay? And then I say that there exists, that I know that this relation holds. So we're going to talk about random, when we talk about random features, it means that we have a kernel and the function phi and a distribution that are somewhat one-to-one corresponding to the other, okay? These are actually very mild assumptions. These kind of maps exist in a ton of different situations. For example, as long as the input set is a measurable space with and you have a measure on it, you can build such random features. And this is just to tell, this is basically the generic notation I'm going to use in the rest of the talk. Okay? If you have these, clearly at this point you can do this kind of Monte Carlo-like approximation. And that's kind of the kernel point of view on this topic. it's kind of useful to consider a more functional point of view. So clearly, if you have a kernel, then you have this old theory of reproducing kernel Hilbert spaces associated to it. So I show you this kind of functional form. But if I can tell you that there is a kernel associated to this, I can also consider the kernel a functional representation, which is basically something that looks like this. I take a linear combination of kernels at points, and then I did it's a clearly linear space, and I can put a Hilbert space structure by appropriately defining a linear product. So standard things, and I'm not going to deal with it. It's not going to matter a lot for my talk. Now you can ask yourself, okay, how are these two representations related? I have the representation in terms of random features and betas, or I have the representation with respect to kernels. How are they related? So let me introduce the other one. So the kernel K here is the limit one, okay? So to do a proper comparison, I have to compare this with somewhat a limit version of the functional representation with features, and this is what I wrote here. So this is the same as my, if you want, is an infinite layer, is a shallow network with an infinite layer. Rather than having finitely many units, or finitely many elements in the sum, I just take an infinite sum. And to take an infinite sum, the coefficients become now a function. Okay? And that's it. So now I have these two function spaces. One is the infinite limit of my random feature network, and the other one is the kernel, and I can try to relate them. And it's basically a basic fact. So here I introduce, so this is the function, and I can put different structure on it depending on the kind of norms I consider on the coefficient function. Okay. Here I put the p norm, but the one we want to consider is just a regular Hilbert space 1, L2. And what you have is that it's a corollary of very standard result, the fact that these two spaces, the reproducing kernel Hilbert space and the space with this representation, are isomorphic and in fact isometric. So it's the same, okay? It's up to you. You have these two structures. You can think about one or the other, but it's completely up to you. You can think in terms of random features, or you can think in terms of kernels, and the two things are completely equivalent. The beauty of this is that it just provides you with a big set of tools, mathematical tools, to understand what's going on. All right, so this is a bit of background about these ideas, but I think a fair question is, what should you care at all? Okay, especially up to now, there's been all really about the functional analysis, the last couple of slides. The main reason is what I told you before. The hope here is that to some extent, at least in some parts, we might be able to replace optimization with randomization, and this may make things much faster. Okay, not completely replaced, but at least some bits of our network are going to be replaced. Optimization is going to be replaced by randomization. And the other thing is that because of this connection, one of the big reasons why this kind of method became popular is because whenever you use kernels, basically now you have a dual representation of your kernel in terms of the random features. Okay? And then you can choose to use this to perform other computations. Here, the number of parameters will depend on the number of points, whereas in the random features kernel, as I'll show you in a minute, is going to depend on the number of random features. So this idea, and I'm going to expand on this in a minute, has been used to provide computational efficient way to perform maximum a posteriori estimate in Gaussian processes, or if you want, learning with kernel methods. Today I'm going to describe supervised learning, but you can imagine that anywhere where you have this kind of kernel methods ideas, or where you want to reproduce in kernel spaces, you could try to apply this kind of techniques. So any questions so far? All right, so what are the properties of these kind of models? This is one quick result, just to tell you what the majority of results have been considering. The majority of effort have considered the approximation of the kernel function itself. Okay, so you have this finite sum, you have this guy, and then you want to know how far they are, perhaps uniformly over a whole set of points. There are a series of results. The one by Sriparumbur and Szabo is probably the latest of a series, and it contains the biggest source of references. There is a whole connection of approximation of characteristic functions in probability theory. These results are nice. Technically, they require some effort. A question, if you want, is, to put it badly, who cares? In the sense, if you want to do prediction, if you want to do learning, why should you care about this? It might be the way to go, but it's also is a big question in itself. And it might, as it turns out, it gives typically suboptimal result. If you go for this question first and just try to apply it, you get suboptimal results.
Is there any reason why here in this theorem you can the approximation only on the diagonal of the kernel?
No, because I was lazy and I wrote just one. No, you can put here. I was still sick and I wrote one. You can put x prime, and do the other one. No. It was doing less with more, but maybe this was not a good case. But forget about these results anyway, because we want to do something else. Okay? What we want to do is that we want to do prediction. So we want to set up our stages with saying what we want to do a bit more precisely than my little dots. So they're going to be a pair of random variables, very standard, x and y. I'm going to fix a loss function, and then I'm going to have some space of hypotheses, and I don't want to minimize the expected risk. Okay? The problem is that I don't have any access to the random variable, but what I have is n copies of my, a sample of n identical independent copies. So the very standard, I don't know what you want to call it, supervised learning, random design regression, or classification setup. Okay, so now you can ask, okay, so what do we know about the properties of the random features schemes in this setting in terms of prediction? And here, the basic results is again the one by Rahimi and Recht. It's 10 years old, but roughly speaking is still holding on as the state of the art, at least until a little ago. So the idea is that we're going to introduce exactly this kind of, so there is an ideal, so when you define the true error, you're going to take the best possible space you can if you have infinite resources, and this is going to be some function of this form, okay? In the setting of Rahimi and Recht, what they considered was an L infinity norm on this. So instead of an L2, they consider an L infinity norms, and this makes the space a little bit smaller than, say, considering L2. And also, they considered a ball. They didn't allow to consider uniformly the whole space. They restrict yourself the ball, and the ball is known a priori to be able to run the algorithm. In practice, sorry for the notation, which is a bit long, but I'm not going to use it too much, they replaced this with their empirical approximation. And what they did is just that they did the empirical risk minimization on this set. Okay? So they consider exactly a network like the one I show you. The only difference is that they consider L infinity or infinity bounds on the coefficients, and then they just do empirical risk minimization. And then they try to check how far this is from the optimum, and this is the kind of result they have. If the loss function is Lipschitz, basically using very standard techniques, what you get is that you get an error which is dependent on the number of features and the number of points. It depends on the radius of the ball that you need to know a priori to run the algorithm. And what you have is that you can get the 1 over square root of n bound, which is essentially what you expect to be the best in this kind of worst case scenario. But you need also a number of features which is linear in the number of points. Okay? This is going to be important for us because if this is really true, then you will not be able to gain any computational benefit unless you are willing to pay a statistical cost. So these results suggest that, as I comment in a minute, that you will have to enter a statistical computational trade-off in order to be able to leverage the good approximation properties. Let me note in passing that Francis basically, a couple of years ago, has a result where he shows that you can get the same, sorry, there is a yes. So you can replace the L infinity ball with an L2 ball, okay? And you basically get roughly the same result. Francis, tell me if I say something wrong. Okay, so this is the basic result, but long story short, that this series of results seems to suggest that unless you make further assumption, there is no way you can get 1 over square root of n rates, keeping a number of features smaller than n. So that's what we were after, trying to see if you can lower the number of features and how much you will lose exactly. So what we did is we will actually make it simpler and just consider ridge regression. So this is just the usual representation, and then we take least squares. So our whole analysis now, importantly, is restricted to least squares. So we're going to use least squares properties all over the place. And we just penalize with the L2 norm. Notice that in this case, sorry, there is a typo here, there is a transpose here. This is, from a computational point of view, now I can show you what it boils down to because it's just a linear system, okay? I have to build the matrix, which is made of the random features and the data, collect the output. I have to form this matrix and then have to invert or solve the linear system, and this is the computational cost. So the computational cost of doing this is the one of forming this matrix, which is going to be nm squared. And then it's basically the cost of storing the smallest of these matrices in memory, which is nm. You can compare this if, to whenever you have a rectangular matrix, you consider the smallest of the two, or either one of two square matrices. If you do the other one, you get the corresponding kernel, and here you get this other cost. So if you were, instead of using random features directly, you were used to use the corresponding kernel, then the kind of cost you would get would be n cubed and n squared. Okay, so that was the main motivation by Rahimi and Reg. Say you want to use the Gaussian kernel, you have to be willing to pay this cost to run your algorithm. But if you're willing to do this kind of random feature approximation, then you can go down to this. Now, if you compare these numbers, clearly what you see is that if n is equal to m, then there is no gain. So if you can choose n smaller than m, then you see something interesting coming up. So to the best of my knowledge, there were no theoretical results showing that this was possible, at least in this worst case scenario. So let me introduce our result. I'll just show you the basic assumption we're making. Most of them are pretty basic. So we make some moment assumption on the noise. We assume the random features to be bounded. This actually can be probably relaxed, but that's just a basic analysis. That's good enough. And then we assume throughout that the best in the class exists. Okay. It doesn't mean that we are considering well-specified models, so the regression function doesn't have to belong to the space, but its projections belong to the space. So there is a minimum achieved. This is not super important, but we can extend it, but let me comment on it later if somebody is interested in it. So a couple of comments, one already made. We're not discarding misspecified models, so we allow the function to not belong to the space, and we consider here not a ball, but the whole space. Professor Duce.
I'm sorry, I'm going to ask about this, which we could take offline. But I mean, if this is like the Gaussian kernel, we know this is a universal approximator, and for general functions in L2, the norm could be, well, arbitrarily large.
Yeah.
Right. So this seems like a fairly strong assumption that this projection exists.
Yeah. Yeah. I mean, if you think of it, so what John is saying is, suppose that you take an analytic kernel, like the Gaussian kernel, then it means that your function, that you're going to find, well, it means that you're willing to give up the true function and look at the best analytic approximation of your function, okay? So that's pretty strong. That's why I was saying you can actually relax this. You can also think that this analysis holds for also other kernels. So instead of the Gaussian, you actually take the exponential. Now you go down from analytic to exactly 2s, 2D derivatives, and then you hit the minimum amount of smoothness you need to get any kind of non-parametric rates, and that's not so bad, okay? So I can show you exactly where in the analysis we use this. This was just to show you one basic set of results where this is going to be true. Okay, so the other comment I made is that, again, we allow here to work on the full, so the radius of the ball doesn't enter the picture right away. We have lambda, but we're going to let lambda goes to 0, and so we are uniform over all possible balls in the reproducing kernel Hilbert space. So this is the face of the result. Let me just parse it a little bit. We're going to have the error of our estimator for fixed lambda. Then we compare it to the error of this best possible model in the class, when if you allow yourself lambda equal to 0 and infinite features. And this is the kind of results we have. So we have 3 terms. 2 of them are pretty familiar. One is essentially a bias term. One is essentially a variance term that depends on the fact that you're regularizing and the data. And then you have the price you pay for random feature approximation. If you now collapse things and you optimize parameter, what you see is that you can choose lambda, order 1 over square root of n, and then you're going to get this rate 1 over square root of n as long as you take the number of random features in the same order of lambda. Okay? So now the number of random features you need is square root of n. You can get exactly, well, you can see it from here clearly. You can get this 1 over square root of n bounds rather than with n features with square root of n features. Okay? So these lower bounds are optimal in this worst case, or they're a limit of an optimal lower bound. If you want, they correspond to the case where you consider exactly 2D derivatives in a Sobolev setting. In fact, Sobolev is a special case of, if you take a Sobolev kernel, this is a special case of this setting. You can use this stuff for classification if you want, but the main point is that there is virtually no difference between a full ridge regression and this model from a pure statistical point of view. one is randomized, but everything holds with high probability. So if I were to give you these two estimators from a pure statistical point of view, they're essentially equivalent. They have no properties that make them different.
There is no difference between a fuller regression. What do you call a fuller regression?
Kernel regression.
Take, if you want, take m, put it this way. If m equal n, let me call that full ridge regression. And I'm saying here that in the regime where m is between square root of n and m, there is no difference.
So somehow I would have expected something like the effective dimension of the kernel to pop in here. And
Yeah.
not see
Again, it's just because I'm working at the, yeah, in the limit here.
And if somehow things are nicer, do you get some kind of result like that?
What Alex said is you have to wait 3 minutes for that. Because I have to go to this part here. Yeah, that's what's coming afterwards, okay? And you see that things are going to be a little bit more interesting. You see more structure coming out. This is the worst case, and let me comment on it. We will discuss it with Alessandro to get an intuition of what's going on. It's weird, this thing, that these random features can work to some extent. Because look, what I'm going to do is that I'm going to take a Gaussian kernel, then I'm going to do Fourier analysis here, and then in some sense I put a measure, and I can have some other properties that govern, you know, the entropy condition of my function space. How come these two things go together? You know, that's kind of what's coming next. So how come that these random features that I build even before looking at the data can do a good job? Well, in this worst case, basically is because they in some sense capture what is the size of the data, which is square root of n. The effective dimension of your data is roughly square root of n in this non-parametric setting. So that's where we stand right now, okay, going exactly in the direction of what you were saying. So we need, we really get a square root improvement in terms of random features, although we keep the same exact statistical rate. So this shows you, this is the first result I know of this kind that shows that there is, for random features, there is a whole regime where you can get computational benefits for free from a statistical point of view. You do not enter a trade-off region. Of course, if you lower that, then you might enter that. Let me also say, super simple, but notice also that when it's obvious, if you want, and in hindsight is classical, but the typical way one thinks about random feature is as a memory budget. It's something governed by the memory budget. So you think of lambda as the regularization parameter, and m as something like your memory budget, how much memory you're willing to spend. But clearly in this equation, you see that the two things, you know, are interchangeable. If you want, you could think of m, the number of random features, as your complexity parameter that governs how big is your model. And then, of course, it's random, so you might need a little bit of preconditioning of your model from a numerical point of view to be sure that the variance doesn't kill you. So if you wish, you could think of lambda as a preconditioning and m as the complexity parameter to control regularization and how complex is your model. And there's nothing to do here because it's just in your head. It's just an interpretation.
I don't understand why you can't handle this conditioning issue by changing the distribution law pi. So you form this matrix capital Phi, you're saying some of its singular values are small, that's why you get a gain by doing ridge regression. But aren't those singular values a function of whatever probability law you use to generate these random features?
Yeah.
Is ridge regression what's really necessary, or are there other mechanisms for addressing this?
Yeah, so what Beck is asking is could you actually, in light of, especially of the light of this last comment, could you just toss ridge regression and put lambda equal to 0? Essentially, what happens here is, I don't know if there is an easier way, but the way I think about it is that whenever you have a matrix of an operator, you want to do a low rank approximation, we know that SVD is the best thing you know, it just gives you the best upper and lower bounds of this approximation. Here, you can prove that you're essentially replacing SVD with a random projection, okay? So basically what happens is that you lose a little bit. Either you either lose a little bit because of this randomness on the upper bound or the lower bound. So you need to somewhat regularize a little bit in order to ensure that even this random projection is aligned enough with the SVD. And to prevent bad cases, you need a little bit of regularization. So it really comes from some sense from the fact that we move from the SVD to some approximation of some SVD, which is stochastic. And some bad cases might happen. So that's why lambda is useful. It's an open question whether you can fix it by designing the distribution in some way, or even more, if you can pick, and this is probably something you could do, projection or random feature in a deterministic way. And that's something I'm going to refer to at the end, in such a way that you can actually be sure that you perfectly align some of the coordinate axis defined by the PCA or whatever you want to call it, SBD. Okay, so I have a couple of slides about the proof. I'm going to mostly skip it, but let me tell you 3 highlights. So one, a lot of this stuff, when you do this ridge regression, even in these infinite dimensional cases, boils down to things that you know when you do linear regression with fixed design. So these are the 2 lines that everybody probably has done as an exercise. And so you see that you do some manipulation, you have some operators to control plus some random variables. So this is very similar to what happens in the infinite dimensional case. Things get a bit more subtle, but that's roughly what's going on. So, you know, basically, instead of the covariance matrix, you have the integral operators, and then you have very similar quantities. You have some quantities that control the noise, some other quantities that control the covariance, and you can pretty much use standard result to control this. You have some basic just operator quantity to control the bias, and for this is very standard in inverse problem and whatnot. The most novel part for us was to actually consider the random feature approximation part. So this is the new part. And perhaps the cutest result is this approximation here. Let me expand a little bit on it. Basically, what we do is that we compare some quantity defined by the integral operator of the exact kernel and some quantity defined by the integral operator of the approximate kernel. Okay? So this is something like an inverse times the operator itself. So it's not quite a projection, but it is a projection in the limit for lambda going to 0. Okay? It becomes exactly the projection on the span of the true kernel and the projection on the span of the approximate kernel. And this turns out to be the key quantity. So you want to control how far are these 2 projections of the exact case versus the projected case. And there is a blessing here that if you look in the analysis carefully, you don't just need the projection to be close. You need the projection to be close after you multiply by this integral operator, which is a smoothing operator, so it makes things better. So if you look at just something like this, or if you just look at basic results on a perturbation theory, you would expect to see the difference of the 2 operators then divided by some gap. If you think of this difference to be order 1 over square root of m, then you might have guessed a bound of this form, and then maybe you say this L1/2 is going to improve things, maybe I get something like this. But in fact, if you do things carefully, basically, if you use something even finer than this, and you have immediately the interplay between concentration and perturbation, you can actually boil this down to 1 over square root of m. And that's where the miracle comes from, if you want, in the analysis, with respect to say, this is what replaces the crude bounds on the kernel with something which is much finer. Anyway, so this is for John, basically. So where are we now? We are in this worst case scenario, okay? This is the end of part 2. And what we know is that we get this 1 over square root of n rates if we're willing to pay this much time and memory. And you can ask yourself, you can do better. You can do better in 2 different ways. Can you do better 1 over square root of n? And can you do better with my n equal n number of random features? The second question we know. I mean, this was just the worst case. So we have to introduce some smoothness condition, and then you can get better rates. We know you can do that. So I'm going to do this a bit quickly because I'm running out of time already, I think. Am I? How much time I have? So basically the 2 conditions are something about how big is the space defined by the exact kernel. This is going to be an eigenvalue condition on exactly, if you want, the effective dimension, the integral operator. This is related to entropy condition on the unit ball of the reproducing kernel Hilbert space, so very standard. Sobolev spaces are the so I introduce a parameter gamma. Gamma equal to 0 is the best case. Gamma equal to 1 is the worst case. So gamma, if you want, you can consider to be d over 2s if you consider a Sobolev kernel on a Euclidean domain. So that's how you match. This is the kind of condition that are standard where you want to go beyond Euclidean domain and density bounded from above and below. They just give you something to work for a probability distribution on some probability space. I consider this polynomial regime. You can consider other regime. You can use an exponential regime if you want to do with Gaussian kernel. You can use finite rank regime, but I'm going to stick to this just for the case of simplicity. This is condition 1. Condition 2 is, again, standard. Is a classical condition from inverse problems. There is called source condition. You can view it perhaps as a sparsity condition. It basically says the following. I have this space, but it might be that the one function I'm looking for lies in a nice subspace of this big space. Okay? And I have to take into account this possible, blessing. So that's what this is doing. It's basically saying, this is one technical way to say it, but it's basically saying if you call f star the conditional the regression function, so the expected conditional, then what you have is that the condition you're making is a condition on the decay of the coefficients of this function on the eigenfunction of this integral operator. So the basic story here is that you have an integral operator, it has eigenfunction, they define a space, this space can be big or small, okay? And then you have this one function you want to write on those eigenfunctions. And that eigenfunction, if it has a fast decay, then this is a very simple function to learn. So it's not quite a sparsity, if you want, is a smoothness, is a decay condition. In the strong sense, if you make this arbitrarily large, it means that this depends on very few coefficients. So in that sense, you can view it as sparsity. And clearly, these two conditions live independently to each other. Okay, you can have a big space and a very simple function, or you can have a very complicated function, but in a very small space. So these two parameters are going to enter the bounds. The case r equal 1/2, and that's where it's basically the exact case of Mercer condition. Okay, there is a characterization of reproducing kernel-based space through integral operator, and that's exactly the case r equal to 1/2. And in that case, that's the limit. That's the worst case. So the case gamma equal to 1, basically the operator is trace class, and the case r equal to 1/2 are the limit case and the worst case. Okay.
Just to be clear, r equals 1 means that f star belongs to your Hilbert space in a nice
No,
way.
this is never f star. So if you want, the point is that here I can always put the projection. So r equal 1, let's say r equal 1/2 means that the projection belongs to the space. So this is what's written, exactly what's written here.
Is there any intuition for r equals 1? I'm just trying to understand the condition.
Yeah, view it like this. I take a Sobolev space with smoothness S, and then which is like 10 derivatives, and then I take one function that actually has twice as many derivatives inside of that space. Okay, so that's a scaling. You know, it's r and r equal 1/2, and 1 will be the scaling with so many more derivatives. So the bigger is r, the simplest is your function. Okay, so this is how the results look like. It's a bit more complicated. Now you have this effective dimension entering the picture. You have some more interesting interplay. I think the one line you might want to look in this whole thing is this one here. Okay, this is the statistical rate you get, which is 2r divided 2r plus gamma, which is exactly the optimal rate. Image minimax rates in the particular case of Sobolev classes. So that's exactly what you were hoping for. This tells you how you have to choose lambda, which is the standard way, and how to choose m. So perhaps let me show you a picture. This is the C tells you the number of features you need. These are the kind of rates you get. Here you have r, and here you have gamma. So these are good cases because gamma. So you have a fast eigenvalue decay, so your space is very small, or your function is super sparse. You're going towards very sparse functions. Okay, whereas that corner is where your space is very big and your function is not very, very sparse. And if you look at the colors, they tell you how many random features you want. And basically, blue is good and yellow is bad. In the sense that if you use yellow, you're close to m equal to n. Whereas if you go down to blue, you can go down to square root of n. So what you see here is that these uniformly sampled random features behave very differently with respect to the entropy condition and the sparsity. They're happy with sparsity. They can exploit it. They can get good rates with few random features, but they're not very happy about small spaces. In some sense, to achieve good rates, you actually have to increase the number of random features. And this is somewhat this effect popping out, and now you have to do structure. The one that you use to define the random features, and then the one that you use to define the smoothness of your function class. In the limit case, they are compatible enough. This is the special case of Mercer theorem, but in general, they might not quite match. And then you can ask, can I fix this? Okay. And long story short, the answer is yes. What you need to do is to use leverage scores. This is an idea that became very popular in dealing with graphs. It was also analyzed in the constant non-parametric regression, and that's the other contribution in Francis Baker a couple of years ago. He basically proposed one way to import this idea from leverage scores for random features, defining data adaptive or distribution adaptive random features. So instead of just picking the random features a priori according to some general distribution, you actually build the distribution based on the data distribution itself, or ideally on the data. So here I give you a pretty theoretical construction. The thing you might want to notice is that at least in the construction I give you, you insanely need to know the true integral operator. Okay, so this is just a proof of concept, and let's just go with it for a minute. So basically what you need to do is that you need to, essentially what you need is to build features, and the features start to look at the eigenstructure of the operator. In some sense, the smoothness, what is going to give you the smoothness of your function start to enter the picture. And that's why this kind of thing is going to work. Now, if you sample things according to this, the results get much better, and in particular, you get the same rate, but now the number of random features is way better. So let me just skip to the plot. The plot is basically, this was the one on the right, and this is the one you have. And this is miraculously better than the other one, because what you have is that here on the parametric case, when you go to close to having a finite dimensional space, you know the number of random features, which is n equal to n. Okay? Whereas here, you actually have order 1, which is kind of what you expect. If you have a finite dimensional space, the number of random features will be roughly the dimension of the space. And that's the constant hiding in this setting. Okay? So it's very different. You can exploit sparsity in both cases, but what you have is that soon as you get these random features, the adaptive one can really see the intrinsic dimension of your problem and adapt to it. When Francis used it, in some sense, he could get an improvement even in the worst case, but here in some sense we shift all the results a little bit up. So in the worst case, he could show that essentially the C he got is a bit worse than this one here. But in some sense it shows that, both results show that the adaptive sampling can give you really something more. And in particular, give you the compatibility to the underlying thing. It also gives right to the obvious intuition, which is how is it possible that random features chosen a priori can adapt so well to simple spaces? They don't. You have to do some more work.
Can I comment quickly?
Yes.
So I do also only cheat losses. You only
Yeah. So as Ben, his results was for any loss function. So definitely this is just I was doing the comparison just for least squares. So if you want, in this sense, an open question is if you do any loss functions, how much of what I told you is going to preserve? We know that for any loss function, you seem to use order n data-independent random features, or possibly better with Francis' results for these data-dependent random features. But can you match instead the results for least squares? That's an open question for everybody. Okay, so that's basically it. So the main take-home message of this is that, okay, we have on the one hand this first result that shows one regime and one setup for which you can get computational benefit with no cost from a statistical point of view. We introduce a set of ideas that can be used in a lot of different places. Kernels appears in all kinds of places. So here you can name the list for density estimation, distribution embedding, kernel PCA, kernel LCA, spectral clustering, you name it, because at this point. And the question here is really if you're going to have this kind of phenomenon. Can you prove that there are conditions for which you can somewhat preserve the best statistical accuracy and decrease the amount of computation? Or this is something specific to supervised learning? It's unclear.
Let's take some time for a few questions.
So in the realizable case, do you think the story will change because the rates might change?
You mean if the true function is in the space?
In the true function is in the space.
No.
It isn't.
No, basically, this paper has been hanging around for a year because we didn't have that case. It turns out that actually is for free. You just have to notice that something is 0 always. So the rates are really kind of the same. You don't really pay a plus for any specification. So unless we go back to John's question, if you take r smaller than 1/2, so if you start to pull your function out, so in the regime I'm considering, which is from inside to even more inside, no. If you consider this case where you start to go out, so your function is very complicated, it's not in the RKHS, then you're going to have worse rate than the well-specified set.
R less than half.
Yeah, so in the R less than half. So in this regime that I show you today, no, it's the same. In the other case, yes, you're going to have a difference for sure.
So in the worst case regime, you still inferior to SGD because you need more memory. In n square times n root n memory. So So at the end, it still shows that kernel feature is still not super useful compared to a more direct approach. Is there any result in between? And you can combine SGD with random features to get the best of both worlds?
Yeah, so
What do you mean by SGD?
So instead of doing ridge regression, what you could do is that you could just run a stochastic gradient descent on kernels. And what you do is that directly on the kernel functions with the coefficients on the kernels. And what you do is that just do one pass, you compute everything once, and then you stop. And because you can just compute and toss away, you're not going to have to store anything. You can do pretty fast, and your complexity is going to be n iteration, the number of points plus the computations. So that's what he's referring to as a quick summary for everybody else. No, you're right. So two things is, even before the SGD, from an optimization point of view, I've done nothing. I just consider a direct solver, so that's insane. And so Alessandro talks on Friday is going to be about taking steps, mixing series ideas from numerics, so preconditioning and fast optimization. So that one is going to give you a better benchmark for what you're saying, and that's something we're looking at now, and we discussed a bit also with Emeric. Multiple pass, one pass review, random features, how far you can go, and it's unclear.
Actually, I have two. The first one is, can you handle the Tsirakov type noise conditions with this?
So that's kind of so these are least squares, right? So what you do for this least squares estimator is that it's just this meta theory for classification, where what you have is that you have this comparison inequalities between the classification risk and the least square risk, and you have these three regimes: the worst case, the margin noise, or the exponential bounds, and then you can just plug them in. So you can take these results, and boom, you can plug them in all these three situations, and you get classification rates. In the worst case, the regression and classification match, but then you can go and gain up to a square root or even an exponential if you are in the hard margin case. So in some sense, you can handle it just because of 20 years old results connecting least squares and classification.
And my second question is about whether, this reminds me of Maury's probabilistic method. Is there a way to recast it as one of those problems for a particular approximation?
Yeah, no, so that's interesting. So Maury Jones, you mean the old lemmas about. So so there is a nice discussion in Ben's papers about this. So essentially here what happens is that this method is oblivious to anything. You just choose. So these are properties that don't have to know anything about the true function, whereas Maury's results as well, follow-ups, are approximation results that assume you can know something, are approximation theory results. So I give you the true function, now give me a randomized approximation, which is good enough. So in some sense, they use some information about this. So they are related, but these are more oblivious than the one by Maury.
And the last quick one for Whit.
Last one, yeah?
So you say that you have no loss of statistical accuracy sort of in the setting that you consider. If I now look at the theory, for instance, that that we have for Gaussian process regression, there are two main sort of theoretical innovations that go beyond what you do. One would be that you actually allow the true function to be approximated from the source and not be actually satisfying the source condition in itself. So for instance, it doesn't have to be in the exact Sobolev space, but you just need to be able to approximate it. And the other one would be, of course, adaptation to the unknown sort of R, and how do you choose a kernel. And I guess if you wanted to achieve in particular the latter, I'm not so sure if you could still retain the computational benefits or are there any...
So the first one I have to discuss exactly what you mean, but I think it relates to... So I'm never assuming here the true function to be in the space, right? I assume I can project it, and I'm telling you I give you the analysis for in case the projection belongs to the space, but it can be relaxed to the, to just be in the interpolation space between the RKHS and L2. Okay, and in that case, you're going to get worst rate 1 over square root, so you're going to have a more interesting regime, but we can discuss that offline. About adaptivity, that's an interesting point. Here I don't discuss it. Clearly, when you start to have smoothness, it's going to depend on it. If you do cross-validation, and if your output are bounded, then you can prove these results, and you just get a log term, and that's it. Okay, so for this supervised setting and just estimating supervision, we hold out cross-validation. Okay, you split the data in two, and at least if your outputs are bounded, it's for free. Adaptation is for free. You can also use Letsky-like method.
Just the first question is, if you take an analytic kernel, so that you have to, so sort of your source condition forces very, very regular functions, and then you take a standard Sobolev smooth functions, what convergence rate would you get in your result?
No, yeah. So it's going to be something that depends on I don't know. That's what I want to tell you today, because this is the case where your function lies exactly in the closure between the reproducing kernel space and L2 space. So that's why I want to take it offline, because I don't remember what I can tell you about. I was commenting on the other point, which is for adaptivity instead, if you're willing to split the data, it's for free. If you're not willing to split the data, then you would have to measure the intrinsic dimension on the data, which is a mess to compute, and then you might lose computational accuracy. And then, yes. So if you're willing to split the data, adaptivity is not a problem here.
Well, thank you. Time for a break.